Thank you very much for the introduction. I put up the QR code here. If you have questions for me, please feel free to add them. Again, Paul Lipman from Infleqtion, delighted to be here again at Q2B, and particularly delighted that this year the scope of the conference has expanded to include quantum sensing, because this is really one of the areas in which we can expect to see real scalable commercial use cases for quantum technology in the near term. It's also a very important part of what we do at Infleqtion. I'm going to talk this morning about a part of the quantum sensing landscape that you may not have heard about before, so I'm hoping this will be an informative discussion. This is the world's first transistor. It was developed at Bell Labs in 1947 and really is the first technology to make use of quantum mechanics. Superconductors, after all, are a quantum mechanical phenomenon, and I'm sure at the time that it was created, the team at Bell Labs could not have imagined how this would transform the world over the next 75 years. We went from the first transistor radios in the 1950s to today, where each of us in the room, I'm sure, has a cell phone in our pocket or in our hands containing tens of billions of transistors. Probably not too much of a stretch to say there's over 1 trillion transistors right here in the room. And so for this breakthrough creation, discovery, the team at Bell Labs were awarded the Nobel Prize. Imagine now a similarly transformed future in which humanity has exquisite control over nature at the quantum mechanical level, where we have the ability to create sensors and devices and circuits which are themselves quantum mechanical, operating at the quantum limit of sensitivity. How might the world again be transformed? Well, in the near future, the ability to create and to control and to measure quantum matter will enable us to create autonomous vehicles that can navigate without GPS to millimeter-level precision, unprecedented levels of visibility into the planet's climate, mineral deposits, and geology, exquisitely sensitive biomedical devices that enable us to detect and to treat currently intractable medical conditions, and solutions to currently unsolved problems in undersea and space-based navigation. And this is just a subset of the areas in which we can expect to see impact. But to do all of this, the first step will require creating quantum matter, and that requires extremely cold temperatures. Now, if you ask the layperson, I'm sure I get a different answer here in the room, but if you ask the layperson, where's the coldest place in the universe, the answer you'll probably get is outer space. Well, outer space has a temperature of about 4 degrees Kelvin, 4 degrees above absolute zero. This is the temperature of the cosmic microwave background that fills the universe. 3 orders of magnitude colder in the millikelvin temperature range. This is the temperature at which superconducting quantum computers operate. Another 3 orders of magnitude colder in the microkelvin range. This is the temperature at which neutral atom quantum computers operate, like the quantum computer in our data center in Colorado. Another 3 orders of magnitude colder, and now we're in the nanokelvin range. And at this temperature, for certain elements, if you can cool them down this far, they take on what is referred to as the 5th form of matter. We have solid, liquid, gas, plasma, and the 5th form of matter is called Bose-Einstein condensate, or BEC. And at this temperature, and this is really the heart of what I'll talk about this morning, at this temperature, if you have a group of atoms, they cease to behave as individual atoms, but rather manifest as a single macroscopic quantum object described by a single quantum wave function, and that has very important implications. If you can create your BEC in microgravity, then you can get even further into the picokelvin range, and this truly is the coldest place in the known universe. This is a picture of astronaut Christina Koch installing the Cold Atom Lab on the International Space Station, which has at its heart very similar Infleqtion technology to what I'm going to talk about here. And this has been continually operating in low Earth orbit for several years. The first BEC was created by Eric Cornell and Carl Wieman in a lab in Boulder, Colorado in 1995, and then very shortly thereafter by Wolfgang Ketterle at MIT. And for this breakthrough landmark achievement, these three scientists were also awarded the Nobel Prize. And today, some 28 years later, I am delighted to announce the launch of Octant, the world's first commercial cloud-based quantum matter service. With Octant, anyone with a web browser can create, can discover, can explore with quantum matter. We're literally making that nano-Kelvin quantum regime available to the world. We called the service Octant because an octant was a navigational device based upon light and optics. And as I'll explain, light and optics are very fundamental to Octant, and also because with Octant you will be able to develop and prototype new kinds of quantum sensors, including in the inertial navigation arena. This is a picture of the actual Octant system in our data center in Colorado. And although the atoms at the center are at nano-Kelvin temperature, the system itself is operating at room temperature. There's no cryogenics, there's no dilution refrigeration. The way that we cool the atoms down is with this piece of technology developed by Infleqtion. The glass cell you see at the bottom there is an ultra-high vacuum cell, what we call an atomic prism. We cool the atoms inside, atoms of rubidium, down to about 500 microkelvin using lasers. And then another laser moves those atoms into the science cell at the top, and then with a subsequent step of cooling, we condense the atoms down until they form a BEC, until they form that fifth form of matter. The graphic on the right shows another part of the system where we can apply an optical potential to the atoms. We literally paint laser light onto the atoms, and all of these steps in creating the BEC and applying the laser potential are all user-definable, either in our web application or through our API. And then once the job has been run, once the experiment has been run, we take a photograph of the atom cloud. And this is really as close as one can get to taking a snapshot of a quantum wave function. This is a macroscopic quantum object, and the picture we're taking is essentially the square of the probability distribution of this macroscopic quantum matter, and that's an actual picture from the Octant system down below. In the late 90s, Wolfgang Ketterle, who I mentioned before, along with a group of collaborators, conducted a groundbreaking experiment in which, for the first time, he demonstrated the interference of BECs, the interference of atomic matter. Now, interference is a manifestation of superposition, and as we know here at Q2B, superposition is very important for quantum computing, as superposition and interference are also fundamental for quantum sensing. You may have heard about or read about the LIGO experiment, the Gravitational Wave Observatory, and essentially what happens in LIGO, and I'm dramatically oversimplifying here, is two perpendicular laser beams are brought together, and by examining the interference pattern, we can detect the signal of interest. In the case of LIGO, a gravitational wave moving through the experiment. Well, atoms have mass. They're sensitive to inertial forces, acceleration, rotation, gravity. And so if we can get atoms to interfere, we can create exquisitely precise sensors for detecting inertial forces. And that was really at the heart of what Ketterle and team were setting out to do here. Now, this took an army of grad students. It took millions of dollars of equipment, no doubt months or years to set up and optimize this equipment. And I'll show you now how, with just a few lines of code in Octant, you can do something very similar. So I'm going to start out by importing the appropriate libraries from the Octant package, authenticating with my Octant API key, and then I'm setting up a barrier. I want to divide this atom cloud into two BECs, and we specify here the width, 4 microns, the duration, 6 milliseconds. These are all user-definable parameters. And then we're going to create the BEC, and I've specified here a target temperature of 25 nanokelvin, 25 billionths of a degree above absolute zero. And you see here a representation of the optical potential with the barrier in the center that I mentioned. We run this, and then we take the snapshot, and here is the snapshot from the Octant system. These are two BEC clouds now that are separated by a few dozen microns. Now, if these were classical clouds of gas and we released the trap, these gas clouds would expand, they'd pass through each other, nothing particularly interesting to see there. Let's see what happens with the actual Octant system. Each frame in this results animation is 1 millisecond, and what we see is the gas clouds start to expand, but then something interesting starts to happen. We're seeing interference patterns emerging. The bright areas are constructive interference, the dark areas in between are destructive interference, and this is completely unique to the quantum mechanical nature of these atoms. Now, I have to say, this looks rather crude. We turned Octant on for public access for the first time yesterday, and already we had a user do something with interference that blows this out of the water, and certainly come to our booth and we'd be happy to show it to you. We're adding additional capabilities to Octant over time, and what I'm showing you here currently is running in our simulator. We'll also be making the simulator available to end users very shortly. On the left, you see this is quantum vortices. So as we drag the barrier across the atom cloud, vortices occur. This is studied in areas such as cosmology and quantum materials, nonlinear dynamics. And on the right, you see a simulation of atom current, which is the atom equivalent of electrical current in the emerging field of atomtronics. As I say, these are actual quantum phenomena that you'll be able to study and explore with Octant. So I've talked about how quantum phenomena can be explored with Octant. Let's talk now about how this is the jumping off point for developing quantum sensors. At Infleqtion, we're partnering with CU Boulder to apply machine learning techniques to quantum matter to create some of the world's most precise sensors. On the left, you see what appears to be an egg carton with marbles inside, which is actually a pretty good analogy for what's going on. It's a lattice of laser light with ultra-cold atoms trapped inside. And we can shake the egg carton and impart momentum to the marbles. We can modulate the lattice and impart momentum to the ultra-cold atoms. And then using reinforcement learning, we can train this system to detect signals of interest: linear acceleration, rotation, gravity, or even a combination. And the beauty of this approach is it doesn't require a physical change to the system. This is real-time, dynamically reconfigurable for detecting the particular signal that we care about in our system. So what I'm showing you here, this is in our simulator. I'll show you in a second in the real system. On the left is a learned shaking sequence. Now, you might be a signal processing expert or a sensing expert. I'm sure we have quite a few here in the room, but a priori, there would be no way to determine this sequence. This was learned using the reinforcement learning technique I was showing you before. The center chart here, this is the results of this 800 microsecond shaking sequence in momentum space. So the atoms start out at rest. We split the cloud, as I showed before. The atoms obtain momentum in opposite directions. They come back and recombined. And if the system had undergone acceleration during the sequence, we would see a distribution of atoms in momentum space as a unique signature of the acceleration signal, and that's what you're seeing here on the right. But in short, what's really happening here is we're applying machine learning to these systems to create some of the world's most precise sensors by taking advantage of the quantum mechanical nature of these atoms. And so here is the actual sequence on the real system in the lab in Boulder. It's a slightly shorter shaking sequence, also for creating a linear accelerometer. Each of the time slices you see is a snapshot of the wave function, exactly as I showed you before. And the power of this approach is the atoms only move a few microns during this sequence. So it provides a pathway for creating very small physical footprint sensors. So in summary, what are we doing? We're applying machine learning to ultra-cold atoms to create dynamically reconfigurable quantum sensors. Because the atoms are held in place in the lattice with hundreds of Gs of force, it makes them very robust to dynamic environments, to deployed environments. In fact, CU is working with NASA to put just such a system into space. You could strap it to a rocket, put it on a submarine, put it on a vehicle. And the work that we've done with CU in the lab has demonstrated more than an order of magnitude improvement in the sensitivity compared to current state of the art. And then lastly, Infleqtion is pioneering the optical systems, the photonically integrated circuits necessary to miniaturize these systems to the point where ultimately they could fit in the palm of your hand. So we're just getting started with Octant. We're really excited to invite the community to use the system. As I mentioned, we've already had users doing incredible things with Octant even in the first day of operation. We're particularly excited to deepen and broaden the access of quantum technology for the education and research communities. And ultimately, our goal is to enable you to create the next generation of quantum sensors, quantum circuits, quantum devices. And the best way to get started is sign up for an account with Octant. Come see us in the showroom floor. We'd be delighted to talk to you about Octant, obviously, and everything that Infleqtion does, from quantum components and supply chain, optical atomic clocks, quantum RF sensors, and quantum computing and quantum software, with the underlying technology really being our ability to very exquisitely point lasers at atoms. Before I go, I just want to give a quick shout out for a couple of sessions that we're doing tomorrow at 1:40 p.m. with our colleagues at JP Morgan. We'll be presenting a new quantum algorithm, QCHOP, for constrained optimization and its applications for ETF arbitrage trading. And then at 2 o'clock, we're presenting with our colleagues at L3 Harris on the topic of quantum radio frequency sensing. So using highly excited Rydberg atoms to detect RF radiation with some very compelling dual use cases. So thank you for your attention. Please feel free to ask questions if you have any. Certainly drop me an email. The QR code here will take you to the Octant sign-up page where you can sign up for an account and start using Octant. And if you'd like to learn more about the applications of Octant, again, please come visit us on the showroom floor. And with that, I'll put up the QR code for any questions that you may have. Thank you for your attention.
Thank you, Paul. We do have time for questions. So please, everybody, shoot the QR code, and they should magically start appearing here on the screen.
They're still wrapping their heads around it. That's the issue.
Yeah. Any questions? Somebody just raised their hand just so somebody's working on a question. Can you put it on the app?
Loading slowly.
Loading slowly.
Do you want to call it out?
Go
we
ahead.
Can repeat it and
call
then
it out.
I can answer it.
So first off, Paul, thank you so much for the presentation. It's very interesting. You mentioned the pathway that you all are looking at to miniaturize and make the system more portable. I was curious how large and heavy it is today.
Yeah, so the atoms and all of the really the guts of the system is an ultra-high vacuum cell. We actually have one at the showroom floor at our desk, so happy to show that to you. And that fits in the palm of your hand. The rest of it really is electronics, which obviously can be miniaturized, and then laser systems. And so that's really at the heart, as I mentioned, of the work we're doing in photonics and in photonically integrated circuits, where ultimately we can take it from an optics bench size to again, something highly deployable. And that's really has been very much at the core of what Infleqtion has done over the years. As I mentioned, the Cold Atom Lab, which had to go on a SpaceX rocket into space and then be deployed on the space station. That contains very similar technology, and we did a lot of work there to deploy and make that system highly rugged and deployable. So that's really in our DNA, and so ultimately, yes, we will get these things down to the size where they'll fit in the palm of your hand.
Thank you.
Here's another question. More on your plans for education.
Yeah, so we're doing a lot in the education area. There's been a lot of interest kind of prior to the launch of Octant, and actually not just with Octant, but with some of our other technologies. For example, in quantum software, we have some technology for magneto-optical traps. And so we're working with a variety of educational institutions, both to create curricula for students, and actually everywhere from the postgrad level all the way down to even into high schools. And so if you are with an educational institution, you'd like to learn about how potentially Octant can become part of your classroom experience, or even a research institution, and you want to be able to use Octant to write papers or write grants, please do come find us and chat with us about that.
Okay, we need to wrap up, but several questions about some of these results you hinted at by your users and other details. Will the people be able to come by your booth and see some of these?
Yes, come by the booth or drop me an email. We'd be happy to chat about anything to do with Octant or Infleqtion more generally.